And as you know that I shall be taking the discrete mathematics course whose subject code is PCCS 401. PCCS 401. And in this course, various topics are there which are apparently they seem to be not connected with one another, but all the topics can be somehow interrelated among one another. So that interrelation part will be discussed later on once you are fully acquainted with the topics. Okay, and as if you have seen your syllabus, you'll get to see, you probably have seen that your syllabus starts with sets and relations and equivalence relation. A topic called equivalence relation is also there. So today my discussion will be based upon this topic, which is called equivalence relation. Okay, equivalence relation. So before I start my today's topic, let me talk about some of the prerequisites which are needed for understanding what is equivalence relation. And these prerequisites I'm writing on the right hand side of this whiteboard. First of all, you have to know what is a set and what are different set operations which can be used to connect several sets. But these things actually you know from your school days, so I shall not kill much time on that. But since to study equivalence relation, the understanding of set and their operations are important, so I'm very briefly on the right hand side I'm writing what are they actually. So first of all, as you know, that set, it is a well-defined collection of distinct objects and if there are several sets, we can combine those sets in several ways. One of the way to combine the sets which are actually known as set operations are union. So if we have two sets like A and B, then A union B is actually known as suppose we say that an element small x belongs to A union B. This implies that the set element is either in set A or in set B. Okay, but this important part, there is a very important point is in this particular type of operation is that since I'm using this connection which is called logical OR, that means when element X is either in the set A or in the set B, then this type of logical inclusion, this type of logical operation like OR is actually inclusive. You have to understand this part very well. Inclusive means when we say that X belongs to A union B, then we can consider this element to be either in set A or in set B or both. But if when we talk and in a literal sense, when we use the word OR, that OR is actually not in inclusive sense. That OR is in exclusive sense. So for example, that particular student is good in his study, or he is not good in his study. This person is criminal, or he is not a criminal. But it cannot be so that the thing is happen. Both the situations can happen for the student or the criminal or the person. You cannot say that this person is a criminal and at the same time he is not the criminal. He is both. You cannot say that student he is good in study and he is not good in study. This inclusive sense is not happening over there. That or either happens either that or this, but in exclusive way, because the both portion is omitted from there. Okay, but in mathematics, when we talk about elements present in a particular set, in a set of the kind A union B, then we say that either the element is present in A or in B or in both. So therefore, this type of logical connection or is actually in its inclusive sense. Second set operation, which is also important, it is called A intersection B, you know very well. And when we say that an element Y belonging to A intersection B, we mean that Y belongs to A and Y belongs to B. Okay, and you very well know the Venn diagram, the figures which we can draw by the Venn diagrams. So I'm not going to draw that. And another operation which we can perform on the sets is like this. If we consider an element Z belonging to A difference B, this operation is called difference. We write it as Z belongs to A, okay, but Z does not belong to B. And lastly, the most important one, and which will be required for our discussion on equivalence relation, is called the Cartesian product, which is denoted by A cross B. It is called the Cartesian product of A, set A and set B. Cartesian product of A and B. And this we define in the following way. So we are considering an element small p belonging to the A cross B. Okay, now the form of A cross B will be like this. The set A cross B is actually the set of all ordered pairs. I'm writing here. The set A cross B actually the set of all ordered pairs. So we define this set in the following way, that A cross B equal to collection of all ordered pairs of the form x comma y, where x belongs to A and y belongs to B. Y belongs to B. So when we talk about P belonging to A cross B, we have to understand that P is not a single element, single point. It is an ordered pair of the form, say, A prime comma B prime, where A prime belongs to A and B prime belongs to B. Okay, so in this way, we define the Cartesian product of two sets. Okay, so this is the most fundamental part which will be needed again and again to understand what is equivalence relation. So I will stretch on that. Okay, now if you ask me that if I like to give you an example on Cartesian product, a very good example. So I can consider the set capital R, which is the set of real numbers. The set is set of real numbers, which we denote by this notation R. Okay, and we can take the Cartesian product of R with itself. Okay, and this Cartesian product is sometimes also written as R2. Okay, or you can say R square. We generally in mathematics, we do not call it as R square, we call it R2. So what does it mean? It means that it contains all the ordered pairs where x is lying between minus infinity and plus infinity, that is the real line. Y is also lying between minus infinity and plus infinity, that is the real line. So that means if we want to geometrically identify what sort of set is this R cross R, we will get to see that it is nothing but the entire Cartesian coordinate plane, Cartesian two-dimensional coordinate plane. So this example, here I have taken the Cartesian product of the set of real numbers with itself. So here also it is a special example of the Cartesian product, which has been defined above and was denoted by A cross B. Here A is capital R and B is capital, and they are both same. So my topic of discussion is not these set theoretic operations. I am not going to solve any problem on that. my topic in fundamental discussion will be on equivalence relation. But before I come to equivalence relation, you have to understand what do we mean by relation. Okay, so I am going to the next page and I am going to start afresh with the definition of relation. Okay, I shall share all the notes with you. Okay, and so if you're slow enough to write these things in your copy, you don't have to worry much. Now, first of all, I'm going to write the definition of relation. And the definition goes like this. A binary relation or simply a relation defined on a set A is the subset of or subset of A cross A specifically. But if I take two different sets for two sets capital A and capital B, the relation or binary relation is denoted by say R from the set A into the set B is the subset of the Cartesian product A cross B. So if I consider the two sets to be same, A and B to be same, then we'll get this primary definition. That means the relation will be defined on the set A and it will be the subset of the set A cross B. So this is a special case of that. And if you consider two different sets, capital A and capital B, in that case, the binary relation will be denoted by R or any other notation you can use. So that relation will be defined from the set capital A to the set capital B, and that will be the subset of the set which is the Cartesian product of capital A and capital B. So this first line is the special case of the second line. So this is called the relation. Okay. For example, I can consider, say, let capital A is equal to 1, 2, 3, and capital B is the set which is small p, q, r. I'm considering, for the time being, I'm considering a very simple example. Now you very well know that the Cartesian product A cross B will be given by this. So if we apply the definition of the Cartesian product, which is written over here, in this case, the Cartesian product will contain the elements of this form. So we'll get elements like 1p, 1q, 1r, 2p, 2q, 2r, and 3p, 3q, and 3r. Okay, now this is the Cartesian product of the set capital A and capital B. Now we are considering a subset which we denoted by this R. I am using two different R's over here. This R, this type of R will be denoted by will be used to denote relation. This type of R will be used to denote the set of real numbers, and this R will be used to denote ring. So this will stand for relation in our class. This will stand for the set of real number, and this will stand for ring. Okay, so three different types of notations we are going to use. So don't confuse yourself when I write these things. Okay, so I am defining a relation. I'm trying to define a relation R according to the definition. So suppose I'm in this particular case, I'm considering these elements which are present in the set R. Say for example, I'm considering 1R, I'm considering 2Q, I'm considering 3P, and I'm considering 3R. So obviously you see that this 1R which is present in capital R is also present in A cross B. 2Q is present in capital this R, also present in A cross B. 3P is present in R, is also present in A cross B, and similar is the case with 3R. So all the elements of R are the elements of A cross B, and you, by the definition, we know that in this case, so and set theoretic rules again comes into the picture. We know that if X belongs to A, implies X belongs to B, and if it is true for all X, then we say that A is a subset of B. Okay, and therefore, since all the elements of capital R is element of A cross B, so that implies, that means that R is a subset of A cross B, and by definition, this implies that R is a relation. R is a relation. Okay. Now, suppose someone likes to consider these elements. Say, for example, I'm considering the element like P1 and R2. So obviously, you can see that this P1 and R2, none of these elements are members of A cross B. This is not a member of A cross B. This is not a member of A cross B. So according to my current scenario, R prime is not a subset of A cross B. And therefore, as I have defined, R prime is not a relation. Is not a relation from capital A into capital B. But if someone considers B cross A, so he will get elements like P1, P2, P3, Q1, Q2, Q3, R1, R2, R3. And in this case, you can see that if I consider B cross A, then P1 is contained in B cross A, R2 is contained in B cross A. P1 is contained in B cross A, R2 is contained in B cross A. And therefore, according to the next criteria, we can say that maybe R prime is not a relation from A into B, but according to that, R prime is a relation from B into A. Okay, so probably you have understood what I mean to say over here. Another example I can consider over here. I'm going to the previous page. Probably you have copied, probably you have understood what I mean to say. So if I go to the previous page, here I considered R cross R. It's a Cartesian product of the set capital R with itself, and it actually defines the Cartesian 2D coordinate plane. So now, if I define a set like this, so for example, I'm considering a set like, which I denote by rho. This notation stands for rho. If I consider a collection of points x, y, where x square plus y square equal to 3 square. So obviously you understand that this is nothing but a circle. This is nothing but a circle. Okay, and I am considering, if I consider x square plus y square equal to 3 square, I am actually considering the boundary points of the circle only. Or if you can consider another set like this, you can consider another set like set which contains all the ordered pairs x, y, which is like this: x square plus y square less than or equal to 3 square. Then that will be considered as, this is a circle, and this will be denoting the circular disk. Okay, in both the case you see that this circle or circular disk, this is a subset of the entire two-dimensional coordinate plane. Okay, so all the points present in this circle, boundary of the circle, or in the circular disk, they are also points of A cross B. They are also points from this two-dimensional coordinate plane, and therefore in both this row and row 1 is a subset of R cross R, and therefore both of them, this row and row 1, both of them are actually relations. So row and row 1 are relations by the definition. Relations from R into R, because here the set capital A and set capital B, they are same, they are equal to R. You can say that row is a relation from R into R, or you can say that row is a relation defined on R. Okay, so this is all about relation. Our topic is about equivalence relation. So obviously equivalence relation is a special type of relation. So let us try to find out what is that. What is equivalence relation? Okay, before I come to the equivalence relation portion, you have to understand that since R is a relation, from the set capital A into capital B, then there must exist domain of this R, of this relation, and image of this relation. So we can define this domain and image of this relation in the following manner. So I have to write the definition. So domain, which we can denote by, say, D of R in short, and image I am denoting by I cross I of R. They can be defined in the following manner. So domain of the relation R can be written as all such points A such that A belonging to capital A and there exist B belonging to capital B such that AB belonging to the set R, and image of R is denoted by is defined in the following way. It contains all such elements B such that B belonging to capital B and there exist A belonging to capital A such that AB belonging to R. Okay, so in the set R, since set R is the subset of A cross B, okay, so its elements are also ordered pairs. So if I consider the element, say, x prime comma y prime belonging to this set R, then all the collections, all the points which appear as first coordinate in the ordered pair, all the points, collection of all the points appearing as the first coordinate of the ordered pair, they constitute the domain, and collection of all the points which appear as the second coordinate of the ordered pair, they constitute the range, which has been mentioned over here. Okay, now With this knowledge on relation, let us come to the important portion, the important definition which I need to discuss, and which is also very important and fundamental. Okay, and it has tremendous amount of applications in all the subject matters of this course curriculum. Now, the definition which I am providing in the following way: definition of equivalence relation. Okay, so what is the definition? Let us write it. Let capital A be a set and R be a relation, R be a relation defined on A, defined on A. So obviously by this we mean that R is the subset of, I'm writing over here, R is actually the subset of A cross A. You already know that. Then R is called number A reflexive, number A reflexive if for all A belonging to capital A belonging to R. One thing I have to tell you about that sometimes for simplicity in some problems you may find, or in some books you may find a sort of notation which may not be like the notation I'm using right now, but I have to tell you that these two notations are actually same. So the notation is, when we say that this ordered pair AB belonging to a relation R, this can also be written as A is related to the element, the point B. And if we say that BA is belonging to the relation R, then in that case we say that B is related to A. Okay, so you have to know this notation. This notation is very important. So this relation R is called reflexive relation if for all A belonging to A, we have that ordered pair A belonging to R, or A is related to itself. Okay, so this is the criteria under which the relation R will be called reflexive relation. The second one is known as symmetric. So the relation R is called symmetric. The relation R is called symmetric if for all A, B belonging to R, for all A, B belonging to R, whenever A, B belongs to R or A is related to B, then BA belonging to R or B is related to A. This criteria is called symmetric criteria. And the last criteria, which is also very important, is given as follows. The criteria goes like this. Number C, it is called transitive. The relation R is called transitive if for all A, B, C, A, B belonging to R and B, C belonging to R implies that A comma C belonging to R. Or we can write it in another way, that A is related to B and B is related to C, implies that A is related to C. Okay, so these three properties are very fundamental. These three properties are we can get relations and we can identify whether these properties are satisfied or not individually. So the first one is called the reflexive property of the relation. The second one is called the symmetric property of the relation. And the third one is called the transitive property of the relation. You can use this notation to check your calculation, or you can use that notation. Either you use this or you can use that. You don't have to, you shouldn't mix them up. Sometimes in doing problems, you are using this notation, and sometimes in the same problem, you are using that notation is strictly prohibited. Either you have to stick to that notation or this notation. Okay. Now, I'm going to the next page. Now I'm writing the most important part. A relation R is on a set A, on a set capital A, is called an equivalence relation, is called an equivalence relation if the relation R is reflexive, symmetric, and transitive. Okay, so all these properties, reflexivity, symmetricity, and transitivity, all these properties, if satisfied by a relation, then that relation R will be called as equivalence relation. And equivalence relations are very fundamental in discrete mathematics. So this type of relation is called equivalence relation. Okay, now let us try to look at this with respect to an example. So I'm taking a problem from the book. Okay, so the problem goes like this. Question number 1. For each of the following relations, on A, the set A is denoted by, is containing the elements 1, 2, 3, 4. Decide whether it is reflexive, symmetric, or transitive. So we have to check whether the following relations, which I'm going to show you, whether they are reflexive, symmetric, transitive, or all of them. The first relation which and before you check whether a particular relation is equivalent relation or not, first of all, you have to be very careful on which particular set the relation has been defined. So suppose in the question, I'm not mentioning this set. Okay, and I'm saying that a relation is defined on something. So this question is incomplete. I don't know, I have to know on which particular set the relation is defined. Then only we can check whether the other relations are equivalent or not. So first of all, we can consider this relation as it is given over here. 1, 3 and 3, 1. Now you very well know that this Cartesian product A contains what type of elements? It contains elements like 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. All these points are present in this Cartesian product A cross A. I think that it would be nice if I write it over here. Although it will kill some time, but since you are doing it for the first time, so it would be nice if entire thing remains in front of you. So the Cartesian product contains points like this. Okay, and now you see that in this particular, the relation has been defined to rho 1. Now, first of all, we can check whether rho 1 is indeed a relation or not. So obviously, since 1, 3 is present in rho 1, 1, 3 is also present in across A. 3, 1 is present in rho 1, 3, 1 is also present in across A. So obviously, rho 1 is a relation. The point is whether this relation is satisfying these properties of reflexivity, symmetricity, or transitivity or not. First of all, immediately we can check that. Immediately we see that points like 1, 1, 2, 2, 3, 3, 4, 4, this type of points are not belonging to the set rho 1. Okay, so the point 1 is not related to, or I have to use this notation, is not related to itself. So therefore, rho 1 is not reflexive. It is not reflexive. But if we consider 1, 3, if I say that 1, 3 is present in rho 1, it implies that 3, 1 is also present in rho 1. So we know from the definition of symmetricity that if AB belonging to R, then it should imply that BA also belongs to R. So from there, I can say that because 1, 3, and 3, 1 are the only points present in rho 1, we don't have to check for other points. So it is true for all the elements present in rho 1. So therefore, rho 1 is also, rho 1 is symmetric. Rho 1 is symmetric, isn't it? So it is satisfying the symmetricity property. But we see that 1, 3 belonging to rho 1 and 3, 1 belonging to rho 1 doesn't imply that 1, 1 belonging to rho 1, or 3, 1, you can visualize this in another way. 3, 1 belonging to rho 1 and 1, 3 belonging to rho 1 doesn't imply that 3, 3 belonging to rho 1. Okay, and therefore this property that AB belonging to R and BC belonging to R implies AC belong to R, it is not getting satisfied over here, and therefore rho 1 is not transitive. Time is running out, so I'm stopping over here. Let us join in the next session when we shall continue with our discussion. Okay, so I'm stopping the recording at this point.